works. Thanks.
Okay. I'm Sam White, and I'll be splitting this talk with Evan Ramos from Charmworks about adaptive MPI. And so I'll be giving a high-level overview or introduction to adaptive MPI, sort of how it works, a little bit of the inner workings, and then we will talk about recent work. I'll talk about collective communication optimizations, and Evan will be talking about global variable privatization tooling support. So the motivation behind MPI is generally that we know task-based programming models like Charm++ can help mitigate variability in its various forms. So that can be software or hardware, things such as faults, load imbalance, differing latencies. Can be difficult to tolerate in an MPI bulk synchronous program. But the challenge then becomes how to adopt a new task-based programming model. So for many of the people at this workshop, the answer has been to adopt Charm++ or another task-based model and develop a new code from scratch. But there's also a lot of existing code out there that's already been written on MPI, or people are already trained on MPI and don't want to give up that comfort. So MPI is our attempt to actually implement MPI on top of Charm++. And so this gives you some of the benefits of both. You get the API and the familiarity of MPI. You can also always take your code and run it on a different MPI implementation, but you get some of the dynamic runtime features of Charm++. The way that this works in practice is MPI virtualizes the concept of an MPI rank. So when you typically in an MPI library, when you launch your program, you specify the number of ranks, which is equivalent to the number of processes. And so if you do MPI run -n 64, you'll get 64 processes and 64 ranks. In AMPI, we separate those two notions of the rank and the process so that you can have more ranks than you have processes. And these ranks become user level threads in AMPI rather than processes. So in this picture, we show kind of like we usually show char array elements in Charm. We have AMPI ranks that are situated on a different PE. And so you can have multiple ranks on each PE. Here you have ranks 1 through 3, or 0 through 3, all sharing the same PE. And in SMP mode, you even share memory across the whole node or the socket. This gives AMPI some opportunities to optimize things. The benefits are things that are familiar to any Charm programmer. So over decomposition, asynchrony, you can overlap one rank's communication with another rank's computation, and migratability. These ranks are actually migratable at runtime, similar to char array elements. And so we can do load balancing with that. Some of the other benefits are with virtualization, we can take advantage of communication locality. So if you have hundreds or thousands of ranks in the same node, we can take advantage of that user space shared memory. I already mentioned dynamic load balancing and fault tolerance as well. To give an example of what MPI virtualization looks like, here we have Lulash 2.0, and on the top we have a projections timeline view of a run without virtualization. And this mini app has a configurable amount of load imbalance. So here we've turned that up some. So you see in the AMPI all reduce purple sections here that some ranks are getting to that all reduce much earlier than others. And the ones that get there later, the ones that get there earlier end up having to wait for the later arrivals to complete the all reduce. On the bottom, we have the same run, but we show a single PE with 8 times over decomposition. So at the bottom, we see this red bar, and that is what's currently happening on the processor. But above that, we see all of these other ranks that are sharing that same processor running in a cooperative fashion. We don't see the purple all reduced time on the main PE bar because we're actually able to overlap that idle time with useful computation. The way that migratability is achieved in MPI is a little bit different than Charm in that we have tried to automate the migration of ranks fully. The way we do this is with a special memory allocator that we call isomalloc, and that reserves a globally unique fraction of the virtual memory space in each process for each virtual rank that could possibly migrate there. The illustration on the right shows that we have this, we have space reserved on each process, but we don't actually have to allocate that. It's just reserved in name only. We are able to migrate both the user level stacks and heaps using this method. And so users don't have to write pup routines for AMPI. We've thought about extending this to Charm++ generally, but haven't quite gotten there yet. It's also worth pointing out that this works on almost all systems we care about now, since BGQ has gone away. The next thing I'll talk about is communication optimizations. This virtualization model of AMPI exposes lots of shared memory between all the ranks and located in the same node, as this picture shows. So if you're messaging from rank 0 to rank 62, those ranks actually share the same address space, so you don't have to worry about crossing process boundaries. That affords us some ability to optimize those transfers. So typically in an MPI implementation, you'll have to, the MPI implementers put a lot of work into optimizing within node transfers via kernel-assisted interprocess copy mechanisms. So there's various forms of these, XPmem on Craze, KNM, Limerick, other more generic ones for Linux. What we were able to do in AMPI was just use user space shared memory. So we don't have to actually have any current special kernel support to do fast messaging between ranks on the same node. This work also motivated the creation of a more generic Charm++ communication interface that we call the zero copy APIs. And these now work for both point-to-point and collective routines. But using this, we were able to optimize AMPI to use the full memory bandwidth on a node for messaging, something that no other MPI implementation was able to do on the system Quartz. Looking at how that affected overall application performance, we looked at the XPAC Center's PlasCom2 code. XPAC is a center for exascale simulation of plasma-coupled combustion, and their code is essentially a stencil code at heart. And they've put some effort into optimizing the MPI and OpenMP versions of the code. But we were able to actually see much better performance, almost a 2x improvement using AMPI compared to the normal MPI version. And this was due entirely to the shared memory optimizations that we implemented. For collective communication, this is more recent work. We've been looking at the Charm++ messaging semantics have both in different ways like hindered and helped AMPI. One thing that we looked at was reducing the amount of memory copies we have to make, and because the previous implementation of AMPI would basically copy out of the application's memory buffer into a charm message and then send that every time. We want to avoid those intermediate copies when we have larger messages. So one thing that we've done is optimize for no-keep broadcasts. No-keep is an entry method attribute that says that the application isn't going to modify the buffer or need it around after the entry method. And so the runtime system can take ownership of that. We're able to optimize that to use a single copy per node. So now when you do a broadcast over a char array, there's only one message created on each recipient node, and then all of the char array elements get a pointer to that message rather than a copy of it. We also added zero copy broadcast support, and this allows us to match MPI's buffer ownership semantics. And for reductions, we're now avoiding CK reduction message creation and copies into and out of that on the sender side. So typically, before you would, every time you contributed to a reduction, you'd have to copy that data into a CK reduction message. But we've avoided that now for reductions that are streamable. Another thing we're working on is revamping sections and the CK multicast library for collectives over them. And this will enable us to more easily generalize our work for MPI communicators of all kinds. So we have some optimizations implemented now for MPI COM world, but we'd like to generalize those to apply to all subcommunicators. The first series of optimizations were for small messages. And so what we did was avoid the CK reduction message creation and copies. And then further, we looked at how to use a shared buffer per node per communicator to avoid having to dynamically create and use memory for reductions. And so we were able to get down much closer to Cray MPI on Cori for a single node reduction here. Whereas previously we were almost 10 microseconds, now we're down to about 3 for 16 times virtualization. For large messages, we switched to using this optimized no keep broadcast feature, and we also are using the zero copy communication APIs for large messages. So these plots don't actually have the small message optimization in them. I just realized, so you can ignore the smaller messages under 4K here, but for large messages, we're now doing much better and avoiding the per rank copies that we had before. The last thing I'll talk about is memory usage of MPI. We looked at multiple kinds of memory used inside of MPI and how to lower our overall memory footprint and reduce the amount of per rank memory that we're using. So one thing is with these zero copy APIs and our fast shared memory communication, we've been able to lower the rendezvous threshold lower than most MPI implementations while not trading off latency, because we're avoiding this kernel-assisted interprocess copy mechanism and its overheads. We've also lifted a lot of MPI's read-only memory storage from the per rank level to the per node level. And this includes storage of built-in things like data types, reduction operations, and groups. The last thing is we've extended the zero copy API from just communication to the PUP migration interface. So we have a new zero copy PUP API that allows you to migrate a char. You could use it for a char array elements, large buffers. You can migrate those in place. So what this looks like in an actual MPI application, this is Jacobi 3D looking at the memory used on a single PE for a one node run on Stampede 2. We've reduced the baseline memory usage of MPI by lifting things to the node level. We've also eliminated the smaller spikes that you see here. Those were communication phases, but now all of the memory that MPI uses for messaging is either pooled in the common case or things are done in place. So we don't actually dynamically create memory for them. The largest spike that you see there is for load balancing. And the spike has been reduced in its height because of the use of the new zero copy API for migration. So we've limited the amount of memory that is needed during a migration phase. Next up, Evan will talk about privatization techniques.
Okay, let me share my screen. Okay, can you see the slides?
Yes.
Okay, so I'm going to talk about automatic privatization in AMPI, and that has to do with global variables. So global variables are the foremost obstacle to running existing MPI codes on AMPI. Anyone who has made a reentrant shared library is familiar with having global variables in your code, but if you need to open more than one instance of it, that will cause conflicts as illustrated by this example code here. Now, new MPI codes can be written with coding standards that avoid the problem entirely by not using global variables. But as far as legacy codes, getting these codes to work is something that's very important for us. So you can see here in this example, each rank in this MPI code would get its rank number into a global variable, have a barrier, so there's some kind of control flow change. And if these were all virtualized ranks in an AMPI program within, say, one process, then the result you get from this print statement is not going to be correct. And that's what we want to avoid. So the first thing you can do if you want to get rid of global variables is to manually change your code. But that is difficult. It can be a lot of time and effort in order to pinpoint all the variables and restructure the code so that you have this extra data that's going from place to place. But one benefit of doing that is that it's completely portable to any system you want without any of the potential drawbacks of the other methods that I'll discuss here shortly. So if we don't want to go through the process of manually privatizing your variables, there are some goals that we would want to keep in mind. And some of the methods we've developed over time have not met these, so we've kept on researching to find new ones. Basically, it comes down to, is it easy to use? Can we cut down on how much work the programmer has to do as much as possible? Is it portable? Does it work no matter what your operating system is or your compiler, or even what version of system libraries are? Sometimes some things require patching the system libraries, and we want to avoid that. That's an extra burden on users that they shouldn't need to do. And as well as, do they also support all the nuances of code, such as all kinds of global variables, all kinds of linking, and most importantly, the ability to migrate at runtime, which is AMPI's killer feature. So we've had some older methods that we still have around. I think the oldest one still in existence is called swap globals, and that's a trick that looks at the ELF structure for your program at runtime and will change all the pointers to the global variables. But unfortunately, this is deprecated now because the GNU linker has broken it, and reinstating it would require some extensive changes to it. It never migrated or worked with static variables in the first place, and it also has a context switching cost that's linear in the number of global variables. So we've deprecated swap globals. And the other first generation one we have is called TLS globals, which uses thread local storage in order to store all your global variables. So all you have to do with this one is add the tag thread local to your variable declarations and definitions. That works for C11 and C++11. Older ones can use __ thread. And in Fortran, you can use the OpenMP thread private directive. This is well supported on Linux and Mac OS, has a constant time switching cost, but it does still have the side effect or the issue that some effort is required. You have to go in and identify variables and make sure they're all tagged correctly. So besides these methods, we also considered what if there's some kind of automated tooling that can change your source code so the global variable problem is fixed in that way. And we have looked at some tools such as Camfort and Fortran and done some work on rows, as we've talked a little bit about already today. But the one we're really looking at is CLang and libtooling. It's a very robust infrastructure for making changes to code. We do have a prototype using libtooling that can add the thread local tag to code automatically, which can make TLS globals more attractive to users. And we are interested in building one that can use the encapsulation method so that there's no dependencies on runtime support, it just works right. Recently, we saw that FLang, or F18, as it was previously known, have been merged into LLVM as of version 11, and we're very hopeful at hopefully being able to extend the support to Fortran in addition to C and C++. So besides those, we've also had some bespoke scripting efforts. Eric talked about his script for privatizing variables and ones for the AdCirc project, and that's another option we have at our disposal as well. More recently, we have a second generation of methods, PIEglobals and FSglobals, that take your MPI program and will build it as a PIE shared object, which stands for Process Independent Executable. And what makes those special is that they store and access global variables relative to the instruction pointer. So if you use these calls as our friends at Riken did, DLM open is a GNU extension to the C library that takes a namespace index, and if you increment it and pass it a new index, it will create a second copy of the program in memory, which will privatize your variables. It will if you call a DLSym, it will give you a different pointer and to whatever entry point it is, and whichever one you jump to is the one that is the context that will activate the global variables, so to speak. So PIEglobals uses DLM open, and file system globals is more of a hack. We just copy the shared object on disk per rank, which is a little bit inefficient, but it has some uses still. And these are being tested nightly on production machines like Commodity Linux, Mac OS, and some Cray systems, and so on. But you can imagine these do have some drawbacks. For example, the DLM interface that PIEglobals uses has a limit inside libc, and it ends up being about 11x over decomposition, which is okay, but we wish we didn't have this cap, especially because it's per process and not per worker thread. So in SMP mode, this level is quite low. You could patch glibc to get over 300, but again, we want to keep user effort minimal. File system globals has its own issues with copying, and it doesn't support shared objects, so that's more of a proof of concept. And of course, neither of these support migration because the location of the code and data segments is handled entirely by libc and the system. So if we wanted to resolve these drawbacks, we could patch the Linux loader. Again, we don't want to do that. Or we could try a new method we've been working on called PIEglobals, which does some things on its own. So it takes the infrastructure from PIEglobals and file system globals. It opens the object once and then uses a different GNU extension to locate all the program segments in memory and make copies of the program for each rank to our isomalloc segments. Then there's a step where it has to scan through the data in order to update function pointers. It's a naive scan, just does this look like a pointer between point A and point B? And if so, do some math to fix it. That has a little bit of an issue. We'll come back to that in a minute. But other than that, without any changes to the user's code, it can become privatized and migratable. So we've demonstrated success with this with MiniGhost and with Neckbone. And we are working toward OpenFOAM and MPI for Pi support, which is very promising. But the method does have some drawbacks of its own, some things to be aware of. For example, there is this overhead at startup. If you went through the effort of privatizing your code manually, you could just run your program, but we do have to do this processing at the beginning of every job. Debugging can be a pain because we are just moving the text segment around in memory. The debugger doesn't know what it's doing anymore. So we recommend debugging without the method if you have to. And then if you really have to, we provide a method compiled into the code you can call from GDB that will take an opaque pointer and try to match it back to where it came from, which might give you the name of a function or a symbol, something that may be a helpful detail for you. The scanning that I mentioned earlier, where we have to find pointers to the code or data, like self pointers, and change them, that can have false positives, particularly in code that does a lot with C++ global constructors and the heap. So OpenFOAM actually runs into this. It opens a lot of script files at init, and it actually falsely matches a pointer. So we want to fix this issue by augmenting our scanning. So it will use the DLM open from pip to open two copies, scan them pairwise, and if it is a true pointer, then the content should be different between them. If it's a false positive, then they should be the same, assuming everything else is deterministic. There is a slight performance issue compared to perfect manual privatization, and that's that the code is duplicated in memory, which causes instruction cache bloat, and is also extra overhead at migration if it's being transmitted over the network or to disk. And we do have potential solutions to these in the works for the future. And this method does require Linux and a GNU userland. So in conclusion, some of Sam's results showed that AMPI is increasingly valuable to different applications, even without load balancing. And we've also made it easier for users to bring their existing codes to AMPI and get some results. We've been working on all parts of AMPI top to bottom, including conformance to the standard and how other MPIs like OpenMPI work, improvements to the communication and memory, making privatization easier, and also reaching out to new application developers. And as Professor Kale mentioned this morning, we are going to rebrand AMPI as Charm MPI to better emphasize the underlying technology and sort of start a family of different projects that are all uniquely identified as Charm. So with that, if you have any questions for Sam or myself, we can take those now.
All right, thank you for the presentation. I think we had 2 or 3 questions on the Google Doc. Phil, do you want to start with your question?
Thanks, sure. First question was for Sam about the reduction optimizations and the comparison to Cray MPI. How much of the remaining overhead of virtualization is just the actual added arithmetic loops of running 15 times more actual reduction computations?
Yeah, so the table that I showed was for a single integer sum.
Okay, so
reduction.
should be
So
pretty trivial then.
yeah, so the most of the time there is likely from the scheduling of 16 ranks on each PE, switching between those.
Okay, thanks. Yeah, if I'm continuing, I guess the other question for Sam or Evan, both for the various privatization techniques you mentioned that potentially involve patching system libraries, are the functions involved amenable to sticking in an LD preload? So you just get, AMPI's version of those functions and the rest of the standard library stays the same?
I think I tried doing that by intercepting mmap, and it would not intercept. The library is internally linked, so you can't do that kind of thing.
Okay, thanks.
And we had one final question by PK Goodla. Do you want to go ahead and ask your question? I can also do it if you want to. So he's asking, are there any performance benefits for developing applications with Charm++ as opposed to going the route of MPI plus AMPI?
Yeah, there's a few considerations, but if we're talking about just performance, I guess the biggest difference would be in AMPI, you're relying on much more on our implementation of things versus in Charm++, you can, in many cases, optimize things more on your own. So if you want to add a group or node group, for instance, to a Charm program to aggregate some sort of messaging within a node, it's a little more transparent in Charm to do that. And there's also a little bit more of what I would call like expressivity in Charm for asynchronous applications. In MPI, you're using the regular MPI programming interface. And there's ways to optimize things by creating communicators via like MPI com split type that are rooted to nodes, but it's a little bit, I guess, a little bit more work at the application level to do that.
If I can add just a little bit to that, I mean, this is a decision that's to some extent subjective. It's a mix of subjective and quantitative decision. So many people, especially in our group, right, think that if you're starting to write an application afresh, they would prefer Charm++. But that's because they're used to programming in Charm++. The MPI has had many people are exposed to it, many people know about it, and so if they might have a subjective preference for it. It has this somewhat anthropomorphic feel to it, right? I mean, I'm a process, I do this, I send, I wait for something, and that's also appealing. The other thing is, I mean, Sam already mentioned some of the other reasons, but the other thing is that you might, for example, think that you are taking a smaller risk by developing it in AMPI, that you or that you want to keep the option open of reverting to regular MPI. That's another reason why you might use AMPI. So I think that pretty much covers it. Anyone wants to add anything? Maybe Phil, do you have a thought?
I think at this point I'm far enough out that I don't get to pontificate about it anymore.
Okay. All right. So I think this is a very important question that we need to address for people about which technology to choose. And you might also ask, why not Charm for Pi, the Python thing, with the same kind of issues. Underlying runtime support is common in all of them. then a lot of it depends on what programming system methodology you like.
All right. There was one final question by Celso Mendes. He's asking if PIEglobals can only be used to G-Fortran. Is that correct?
So it doesn't have to be compiled with G-Fortran. If you have a compiler that can output as PIE, that should be all it needs. But what you do need is a GNU userland, so like glibc and the GNU tools and that kind of thing. But G-Fortran is not a hard requirement, no.